Okay, so this is an example of linear program. And basically what we're doing here is we're trying to, I think this is producing some sort of animal feed, um, bird seed, and the bird seed needs to actually be a mixture of these different possible seeds. We have everything from sunflower seeds to grass seeds to wheat and cracked corn. And we need certain nutritional values. Our overall finished product in 1 pound, we need to have it at least 13% protein, at least 15% fat, but less than or equal to 14% fiber. I thought that if that was humans, you'd want it the other way around. You'd want it to be healthy. But anyway, that's so we have basically minimums on line 13 and maximums on line 14. We have the cost per pound. Now, what's quite nice about this and why we don't, it's simpler than we think, is that we're basically thinking we're doing a mix for a pound. So these are the decision variables here. And basically, the total needs to equal 1. So let's just have a total cell here that basically sums all of these up. And then when we get to solver, we can actually set this to 1 for 1 pound. Now, we need to find the cost of this pound. And what we would basically do is we would kind of have our pounds and here, and then we'd multiply it by the cost of the pound. And the idea of our optimization problem is we want to find the minimum cost for the combinations that meet the requirements and limitations. So the cost, I think I didn't remove that, but let's just do that from scratch. We're going to use sum product, and it's basically going to be sum product of the pounds and the costs. And you can see it's 0 at the moment, but if we had a pound of sunflower seeds, and that's 0.22 per pound, then that will be 0.22. Okay, beautiful. Now we need to find the protein, the percentage protein in the overall food. And the nice thing is that we're weighting it to 1 pound is we basically just do a weighted sum. What proportion of the pound is from each ingredient multiplied by the percentage of protein, and then we get the aggregate protein for this mixture. So this again is just going to be a sum product. And it's going to be a sum product of the pounds and the protein. And then, of course, we're just going to follow for the fat and the fiber. Okay, so we've got the sum product here. And we have fat. And then select again, and fiber. We just want to actually check that. So let's just check these equations. So we can see pounds times protein, pounds times fat, pounds times fiber, and our objective function is pounds times cost. Okay, so now we can actually go to data, solver. Our objective is we want to minimize this time the cost per pound. And we're going to do it by changing these variable cells. Basically, the amount of each of the types of seeds in the mix. The first constraint we're going to add is this constraint that makes everything a proportion, that we have one, we do it on the sum, that we have 1 pound. So our total pounds is going to be equal to 1. And then we have our greater or equal constraints. The protein and the fat are greater or equal than 13 and 15% respectively. And our less than constraint, our fiber, is less than or equal to 14. Just check that. Fiber F22 is less than or equal to E14. Okay, good. So we have our different constraints here. It's a linear program, so we use the simplex, and we're gonna solve. Now, unfortunately, we're not feasible, so we're gonna add some feasibility reports. And I'll tell you why it's not feasible in a second. But you can see here that they're pretty much, the feasibility reports are pretty much the same thing. Let's just delete the second one. You can see that the constraints here, we're violating the kind of the fat constraint, but the fiber constraint is also bound. And that's kind of the issue here, that they're kind of operating against each other. So we've reached the fiber total of 14. If we reach the fiber total of 14, we get a violated fat constraint. So that's the feasibility. But I can just okay. So let's kind of look back at our model here and see what the issue is. And the major issue here is that if you look, we need to have a certain requirement of protein and fat. We need 13% protein, 26% fat. So to do this, you know, most of the kind of the types of food have much lower values than this. So we're going to need a fair amount of sunflower seeds, and we're going to need a fair amount of safflowers because they have like higher protein and fat than the requirements. Well, most others have lower values. But at the same time, the safflower and sunflower seeds have huge amounts of fiber, which violates the fiber constraint. So they're working against each other. So what we're going to do is we're going to relax this constraint a little bit. We're going to make it 14.5. And we're going to see if this actually gives us a feasible solution. And let's just remove, we don't want too many of these reports messing around. Let's just remove these reports. And let's go back to our solver. And our model should still be there. And the nice thing about us not hard coding the 15% and putting it in the cell, we just update the cell, the model's the same. So we can just click solve. And voila, we now have a feasible model. Let's just kind of get the answer and sensitivity sheets. But we can see here now, we have sunflower seeds, oats, and cracked corn. We have a cost per pound of approximately 15 cents. You can see that the fat and the fiber constraint are bound, but we're just quite a bit over on the protein constraint. So it's like the fat and the fiber are working against each other. We can look at the answer report, and again we get this here. You know, the protein constraint is not binding, but our fat constraint is binding, and our fiber constraint is binding. And we can kind of look a little bit at the kind of the sensitivity analysis report. And remember, I talked a little bit about this idea of shadow price, and we can see that let's just have a look. So for each increase of 1 in the fat that we're allowed, we would actually each increase of 1 in the fat required, this would actually increase our cost quite significantly. And for each increase of 1 in the fiber required, that would decrease our shadow price quite significantly. Now, these are very big values simply because we're dealing in very small proportions here. You know, we've got 0.145 and 0.14. And the other thing I just want to mention, you see here we've got the sunflower seeds, and we have the oat pounds, and we have the cracked corn pounds. And what the reduced cost says is basically the decrease required in the objective coefficient to allow us to add that into the model. So that's the answer report and the sensitivity report. So let's just actually put this in our kind of solution thing to the right. So just copy, and then we're just going to paste values. And then we have the cost per pound, protein, fat, fiber, and again, we're going to paste values. And now what we're going to do is we're going to compare this with a model where we're going to remove the fat back to 15%, but we're now going to relax this fiber constraint, saying that rather than 14%, we're going to have a limit of 14.5%. So this is going up this time, but that's because it's a limitation. So we're allowing a little bit more fiber. So let's go again. Solve the same model. And again, I kind of showed you the answer report. You can see the fat and the fiber are still binding. We can see here the shadow price. So we can see that because of the constraint, the total pound really doesn't mean very much. But again, increasing the fat total by 1 increases the price, the kind of the fat required increases the price by 1.15. But we only have a very slightly allowable increase there. And again, with the fiber, increasing by 1 decreases the price because again this is a constraint going in the other direction. So if we allow more fiber, then we have a much more relaxed model. But again, we only have this very small allowable increase. So let's kind of go back to this. So we have our solution. Again, it's pretty much the same cost and it uses the same variables. So the same foods, but just slightly different proportions. And again, we can see that we've got slightly different fat and fiber values, but we still are hitting those constraints at the fat and fiber values. The protein is not hitting the constraints, but the cost, this model is not quite as good. The costs are a little bit higher. So just to summarize, we had this model. It's just a very standard mixing model. It was not feasible. So what we did is we relaxed it a little bit. First, we allowed, we had a requirement that we can't have more than a certain amount of, we had a requirement that we must have a certain amount of fat. And we actually relaxed that a little bit to say we don't need quite as much fat, and we made it feasible. Then we had a limitation on the amount of fiber, and again we relaxed that a little bit and made that limitation a little bit higher, allowing a little bit more fiber, going from 14 to 45. And again we got another feasible solution, and then we compared the two feasible solutions.